Can you hear? Yeah. Hello. Yeah. As Justin said, we're gonna quickly having this talk about Poseidon. I'm gonna do a quick survey of about 10-15 minutes about some attacks in the last years of Poseidon. About the first idea of Poseidon, as Dimitri in the room, was like in 2018 discussed at DevCon about that. Quick notation: I know some of you are maybe jet lagged or it's the first of the day. Like I marked the slides that are more important with the red stars. The rest of the time you can sleep. So this, I just want to highlight that we have this Poseidon initiative that started like last year, that is led by Dimitri, and me and George were giving some help. And this is a mix of us, Justin said, of battles, a workshop, and attacks, bounties on Poseidon. And we as well like to try to be a bit more neutral, because we have this kind of, let's say, central role of with having Dimitri as well, one of the creator, and that works at the Foundation. We have as well this neutral advisory board with big names in the space like JP or Elements and so on, Tyra and so on. And we plan to end this initiative by the January 2027. So this is like a recap of the initiatives. We have bounties. We have research grants that we get this year. We did 3 workshops. We'll do the 4th workshop in about 2-3 weeks. There's some special research awards, do some special papers, and we have some other bounties not listed here. I think there is like that is really tight on Grosvenor basis, and it's about 600K for 2025. For 2026, I think we're still in discussion on the budget. So I said the Poseidon function was actually formalized in a paper in 2019 by Lorenzo Grassi, Dimitri, Christian, Roy, and Mark. And for people that never seen it, it looks like this. I will not go into details. I think, I hope that many of you have seen this already, but it contains some easy operation in some field over FP. This operation are some matrix multiplication, some addition that is marked with the RC, and S is the non-linear part of the function that's called S box, that for us, before Justin was said, for Qualiber is exponentiating a field over an exponent tree. And yeah, this is the degree of the S box that change depending on the prime chosen. For Qualiber is 6, so for Qualiber is 3, and the number of round is the number of the full rounds that are a bit more heavy and are less, and the partial round that are the one marked in the middle. As you see, the partial rounds have a different matrix because it's a different color, and the S box and the constant addition happens only to the first line and not to all. In the course of this year, we have seen some attacks on reduce around, and actually there are like 4, at least like 3 values of possible attacks. Of course, like you can start to brute force and try to guess outcome of this function. Then you have statistical attacks. But today in this talk, we cover only some algebraic attacks, and basically like you can split the attacks in 3 ways. You have like interpolational attack, and we will see during this talk that it's about solving univariate polynomial or bivariate, or in a more complex situation, you want to use like the atomic bomb that is Grosvenor basis. In the algebraic attack, in order like to kind of simplify the attacker perspective, the author of Poseidon, they formalized this problem that's called a SICO problem. That is constrained input and constrained output problem, and basically like you fix some 0 in the input and the output. In this case, like the last state is 0 in the input and the output. If people are able to solve this problem, and what we challenge in the bounties, what it means is funding a pre-image attack. And yeah, for example, some of the bounties were about solving the pq1 problem. So meaning pq1 problem means that actually the 0 to fix is only one. So you have like 1 0 fixed in the input and 1 0 fixed in the output. And the way you try to formalize the attack is that is kind of the natural way is you run Poseidon in a way that you map the first input to an X, and you actually run through Poseidon. At the end, you obtain in a symbolic way a polynomial X in the final states. And basically, if you fix and try to solve Px equals to 0, it means that you find a solution to this like polynomial, and you basically you have a pre-image for like at least for the last 0 of the Poseidon. So this was kind of well known, but the first one to actually formalize this attack was in this paper by Barend, Bouvier, Laurent, and Perrin in 2022. And it was as a response of the first attempt to have a bounties in Ethereum, and it was done, I think, in 2021. And the way they did it is like in this kind of standard way, at least in finding roots of polynomial. And there's a variation of the Rabin or Cantor-Tassenhaus algorithm that is actually you just need one root, while the more generic algorithm they actually focus on finding all the roots of the polynomial, but in the case of Poseidon, you only need one root. And the algorithm is actually works in this way. You basically you compute this polynomial over this the algebraic closure of this ring, and it's like xp minus x. This contains all the solution to the algebraic closure, and basically you compute the GCD between this new polynomial and your original polynomial, and of course this will have a new polynomial that contains the solution of the polynomial you want to solve, and you basically factor it. And the reason you can factor now is because this new polynomial R is actually a low degree. Usually it's a maximum degree 2, so it's really trivial. Indeed, if we map how much this costs, the first cost is the most heavy one. So the first and the second are kind of driving the complexity, the asymptotic complexity. And yeah, the notation here is that MD is the cost of multiply a polynomial over FP, and this actually depends how you do it. It can cost like if you use Bluestan, it actually costs a bit less. So I said this was done, and in the previous version of the hash function cryptanalysis competition in 2021, they contain other hash function, not only Poseidon. The authors of the previous paper, they were able to break some bounties on the reduced round of Poseidon. And yeah, but the question now is, can we actually do better than this? So indeed, like the prime that we use in Poseidon, they're not like random. They're kind of they have some special properties, right? And my answer is yes, we can do actually better than that. And how? So basically, like the idea, and you will see in the next slide that I'm actually one of the authors of this, that we use this idea, is we leverage this paper of 2015, Algrenet, Van der Hoven, and Leserve, that basically use this really fascinating construction of the 18th century called a graphic transform. And the graphic transform is, in order to work really good, you need the prime to be in this special form, and we'll see that actually the prime we are using, even in Qualabert, is of this special form. So quick introduction of the graphic transform, how it works. Basically, the graphic transform of a polynomial P, it works like this. You take your polynomial and you apply this graphic transform that give you, so the polynomial P, it gives you as an output a new polynomial G that has the same degree of P, but and the way how you do the transform is multiply the polynomial at Z, and you multiply with the polynomial at minus Z, and you evaluate at the square root of Z. Hold on with me a second, and I will show you that it's kind of useful. But before then going ahead, the things to pay attention is this. Imagine that you start from the polynomial, and alpha I are all the root of the polynomial. what you actually obtain with this transform, you obtain a new polynomial of the same degree of p, but actually is the multiplication of the square root of all the roots. I mean, the magic things of graph is that you don't know alpha. The root of, you don't need to factor the polynomial and knowing alpha in order to actually having a new polynomial with the square of the alpha. This is kind of really magic to me. It's kind of working homomorphically on the roots of the polynomial without knowing that. And this actually turns to be useful, and I just sketched the idea of the polynomial, and it works like this. Again, like the prime is of this form, so of the special form, and you have S that is like p minus 1 over r, and you basically you compute the graphic transform of this original polynomial. You can do n times, and because you can actually compose the graphic transform, and then you have this polynomial p tilde that is the multiplication of z minus alpha I r. And once you do that, you can actually use the Fermat-Littre theorem, and you have this observation, like you have a beta I that is like alpha I to the r, and what you actually obtain is that you are doing this. This means that the root of this n-time transform of graph transform is actually the S root of unity because of the application of Fermat-Littre theorem. And now actually you are working on a subgroup, and you can actually brute force the roots of this special polynomial. And yeah, as a result, you actually found the roots of p tilde. But actually you're not interested in the root of p tilde, you're interested in the root of p. How do you do that? You better ask me if you're interested after this presentation, because it's a bit longer, but I can assure you that you can do easier than the original polynomial. So the question is do we have suitable bound instances, or do we have suitable prime that we are interested in? Yes, one of these is, I think this is called Goldilocks prime, and this of this shape. Actually, even the Poseidon 256 challenge, this is the scalar field of BLS 12381 has this form. And I said, we have this paper that I think it's going to be in the print in the next couple of days, where we are using this attack to break Poseidon bounties. Now, specifically, we broke all the bounties, 3 of the 4 bounties on Poseidon 64, because this attack is actually 3 orders of magnitude faster than the previous one on that used the Zassenhaus algorithm. And actually, a specification here, I say we broke is kind of cheating, because I could not break the Ethereum bounty because I work at the Ethereum Foundation. What actually happens is we're working on this without knowing each other on this idea in parallel, and actually the people that broke the bounties are Jintai and Tsiu, but we actually eventually, since it was the identical idea, we decided to merge the papers and do a single one. But technically they broke the bounties. I didn't get any money, of course, out of it. And here it shows that our attack is actually 3 orders of magnitude faster than the previous one. That is, as you see, this the 7 is the paper that I showed before. As this is really 3 times faster than more or less than the previous one. Just because we are using and leveraging the shape of this kind of primes. Now this showed how to solve the pq1 problem, but what about pq2 problem? So what about if there are 2 0? We map 2 0 rather than 1. That is actually what we are interested. Because in order actually to break Poseidon for real, you work on pq5, pq6 problems. So, but let's check pq2 problem. So basically, in this case, you follow the same pattern before. You are mapping symbolically the first 2 input with x and y, and you're fixing the 0 0 in the input, and you try to solve some system of bivariate polynomials. So you have p and x with these bivariate polynomials, and you want to solve it. And of course, you could use Grobner, but actually there is a more clever way to do it. And this was applied by Barian, Boeuf, Osteller, and Zalzeron. And actually, the date is incorrect. It was 2025. It was as a result of again the bounty challenge we proposed at the Ethereum Foundation. And actually, they're using this theorem that the polynomial pq share a common root in the algebraic closure if the resultant pq is equal to 0. And just like technically, what is the resultant is the determinant of the Sylvester matrix of P and Q. Again, like for details, you can catch me after this presentation. And what they did, they solved many of the bounties on Poseidon 31, and we have two actually instantiation of Poseidon 31. They are like koala pair and M31. So they actually did a great job on claiming many of the bounties. And yeah, for the rest, like what about generic problem? So for generic problem, use again, I defined that before the Grosvenor basis anatomic bomb, and indeed, like I'm not going to discuss about the Grosvenor basis now. If you have any question, like you can catch me after the talk. But basically, like you apply this generic attack for any K, basically, and it's should be the fastest one for now. If you have a better idea, indeed, like I have some open problems for you. Like if you want to discuss about any of this in the Poseidon workshop, I think it's in a couple of days. So one of the questions is like, can we actually do better in Grosvenor basis for SICO3 and SICO4? Or can we apply the graph method for bivariate polynomials? Or can the interpretation attack be improved in any way? And that's it. I don't know if I have time for questions, otherwise I'll leave the word to Jacqueline.
One question.
Sure.
I was saying we have time for one question. Who wants to ask a question? I didn't know about the recent breaks. That's pretty cool. How good are you feeling about Poseidon?
Well, better and better every day. Sure.
Oh.
Yeah, I was worried about small fields because Poseidon originally was like thought to be work like on bigger prime, like 156 bits. Lately we shift our attention on smaller primes that are like 31 bits. I was worried at the beginning about it. I'm gaining some confidence as we go.
Excellent. Thank you so much, Antonio.